Hello, everyone. Maybe good morning or maybe good night. Thank you for joining this session. I am Kokolo Ikeda from JIST, and I will serve as the session chair. This session focuses on Go and its variants, NoGo or Killall-Go, with 3 presentations. Each presentation includes a 15 minutes talk and a 5-minute Q&A session. Please ask questions or share comments via the chat box or verbally. If you wish to ask verbally, please use the raise hand button, then we will unmute you. If using the chat box, it's helpful to write down your question during the presentation, but please send it only during the Q&A session. Okay, the first presentation is analyzing KataGo, comparative evaluation against perfect play in the game of Go. Presented by the second author, Professor Martin Müller. Please share your slide and start the presentation.
Hello, can you see my slides and hear me?
Yes, please start.
Okay, so thank you for the introduction. This is the work done by my master student, Asmaul Husna. And so the title kind of gives an overview of what it's about. We were interested in how good a strong open source Go program like KataGo plays. And of course, we know it plays better than all human players, but in the limit, how well does it do against perfection? So let me just jump right in. So everyone knows, of course, the successes of AlphaGo, AlphaZero, and programs that were designed based on them, such as KataGo. And so, yeah, we know they're all super strong players, but we kind of try to push it to the limit and see in the cases where we can actually compare with perfect play, how do they do? So that's the big picture behind our talk. And here's some more detailed questions. So the first question is just comparing different versions. So this is related to the question, how does it learn? So we looked at several versions of the KataGo program. The main thing it learns, of course, is when during training, it learns a stronger and stronger neural network. And so we just took an intermediate level network and then the strongest available network at the time of these experiments. And the other thing you can scale other than the training is the search. So we looked at both results without any search, with a small search, and then also scaling further in some cases to a larger search. And like I said before, the measure of success is the strongest possible measure, right? We compare KataGo against an optimal player. So now you may be surprised, right? Because in the game of Go, it's very, very difficult to play optimally. And I will talk about the special cases where we can do that. And then further on, I'll talk about the 2 different criteria. What does it even mean to be optimal? And one comes from combinatorial game theory, which is called incentive optimal. And the other one is the traditional minimax optimality, which is the highest possible score of the game. All right, so this work was motivated by a number of previous works. One was by my previous student, Rejwana Haq, and she did similar experiments in the case of chess with the program LilaChess 0, which is also an AlphaZero derived program that's a strong open source player. And in the case of chess, we have a big advantage over Go in the sense that we have these endgame table bases, which are a wide variety of positions from very simple to extremely difficult, for which we know perfect play. And we can, in that work, we researched the limits of Leela Chess Zero in these endgames for which we can compare them with perfection. And found a few interesting things, such as when the original move policy is correct, but then the search makes it wrong. All right, the other motivation for this work is the experience from the game of Avari, which has been solved over 20 years ago, but I think the findings are still relevant for this case. At that time, the strongest Avari playing heuristic programs were assumed to be almost perfect. So when they played against each other, it's usually very close games and nothing much happens to the evaluation function. However, after Romain and Bal solved the game by building the complete database, they found that both of these super strong programs still make a considerable number of errors, right? So both of them were quite far from 100% correct, and they made many game-losing moves in the analysis. All right, so these are motivations to check out what about these super strong, deep neural net-based programs? Are they perfect, or what are their errors that they still make? Okay, so yes, we did have an exact solver for the game of Go, but only for special cases in the game of Go. I'll talk about it in a minute. There are special endgame positions in Go that we can solve with efficient algorithms based on combinatorial game theory. And then, yeah, we did a similar study to the previous chess study, but for the game of Go. So we looked at how KataGo does without search, with a small search, when we scale the search, and also how well is it able to find optimal moves by these two different criteria of what optimality means. All right, so a little bit about the exact solver and about the difference between these two concepts of optimality. So the incentive is a very familiar concept for people that know combinatorial game theory. The incentive measures the difference between the position before you make the move and after the move. And that difference you can express as a value in the sense of combinatorial games. And if there is a move for which this difference is better than for any other move, then we call that an incentive optimal move. So in the example here, there's a single move that in the sense of improving the position is better than all others, and that's that move F4. And so that gives us an efficient playing algorithm. If you find a move for which the incentive dominates all the other moves, then you don't need to do a search anymore. You can just play that move and it's guaranteed to be optimal. Unfortunately, that doesn't always happen. And so if you have different moves and none of them dominates the other, then you're back to the standard minimax search. And in general, the notion of incentive optimal is stronger than minimax optimal. Like in the example here, there's only a single incentive optimal move, but there are many other moves that lead to the same minimax score for the whole game. All right, so this is an overview of what Asmaul did. She used an exact solver to find optimal play in Go endgame positions. And she also developed a larger data set than what we could find in the literature. And then did these performance evaluations that I talked about and looked at some interesting cases as well. Okay, KataGo is right now the strongest known open source Go program. So it's very famous, used by many, many people, including many professional players. It started out as an implementation for AlphaZero for the game of Go, but then there were many improvements to further improve KataGo and also to make it more versatile so it can play with handicap, with different kinds of komi on different board sizes and different types of Go rules. So it's a very popular tool, and therefore we chose this one for our experiments. So let me talk about what exactly we did. So our original data set is from the famous book by Berlekamp and Wolf called Mathematical Go. And in that book, 22 endgame problems are introduced and analyzed. Many, many years ago in my PhD thesis, I wrote a computer program to solve modified versions of these problems. And the problems are modified in a way that a computer can do all the steps automatically, which is not feasible for the original problems because they have like stones that are not clearly alive in two eyes and things like that. So there's a certain mix of endgame and other parts of the game of Go, whereas in the modified problem, these things are clearly separated. All right, so since the data set was still small, basically two versions of 22 problems, we created an extended data set by using the exact solver on these starting positions and basically play what we call a perfect game where we play both sides with the optimal moves. And that gives us a larger set of somewhat easier positions, right? The original position is as hard as the problem itself. But then as more and more moves are played, typically these problems become easier and there's fewer moves and less complicated positions. All right, so that was our extended data set. The other extended data set, again, similar to what I did in my PhD thesis, was to take one of the largest problems from the book and just removes many of these small endgame areas by just playing out these parts and leaving only a subset of the original endgame areas. All right. So I talked about incentives already. So since we wanted to study how good the neural networks are in finding best moves with best incentive, we split our test set into the two cases. Either there is a single dominating best incentive or there is not. And so we did different experiments on these two types of sets. These are all the neural networks that we used. The details of the strong network, this was the best available at the time. The weak network is a lot less deep and less broad and also less training done on it. Okay, let's see what happened with our experiments. I'll go to the summary. So this is evaluating how many of these problems were solved in the sense of playing a correct move. And we considered, since we had the exact solver, we considered all possible correct moves. So on the original data set, without search, this is the first table, the weak policy solved 40%, the strong policy solved almost 60%. And very similar results for the modified problems because they're basically the same in terms of play. Whereas the perfect game and subset data sets are much easier because they contain a large number of simpler problems. Okay, so this is just the raw policy without search. So you can see the improvement from the left side to the right side between the weak and the strong policy. Now let's see what happens if we add a small search, just 100 nodes. The weak policy doesn't get that much better, right? So the improvement is just a few percents. So whereas the strong policy, you find for the first two sets, stronger improvement. And for the other two, they're almost close to 100% already. So I think this is strong evidence that the longer training also leads to a stronger search performance, right? It learns not just better value or policy net, but it also learns a better search in general. Okay, this is the scaling experiment where we went from 100 nodes per position all the way up to over 100,000. And you can see the accuracy, which is the number of solved problems. It increases as one might expect. For the weak policy, it's very noticeable. For the Strong policy, it's maybe surprising. It seems to plateau early on, and it means that the remaining problems are out of reach for KataGo, at least within the limits of what we tested. Okay, right. Back to this division of the problem set into best incentive and minimax optimal moves. So let's look at the difference here. And the difference is quite massive. So even when KataGo can solve 100% of the games in the minimax optimal fashion, it very often does not find the incentive optimal move, which makes sense if you know how the programs work. But it's interesting that apparently the policy network is not able to pick up on the fact that some incentive optimal moves are really better than other moves. All right. Let me skip to the next step, next experiment. We also compared whether KataGo can actually win in these endgame positions. They're all constructed that you have to basically play each move perfectly in order to win the whole game. And as you can see, for the perfect games, there's a considerable number of positions, 11, where KataGo played a losing move at some point or another during the game. Here's one example. You can read the details in the paper, but KataGo basically makes a mistake pretty early on and is then in a losing position. Okay, let me wrap up. There are some other interesting cases where both the longer search and smaller search are wrong. And if you look at the stats, the short version of these slides is the stats have no idea whether a good move or a bad move is better or not. So the win rates and all the other measurements, they just show basically random fluctuations for my eyes. Okay, let me conclude. As expected, maybe adding search significantly improved the performance and got these programs closer to perfection. It's more focused on actually using search to solve these positions as opposed to just learning a super strong policy, which would immediately find the best move. So we have some simple positions where that doesn't happen. Okay, let me stop here. I'm over time and take some questions. Thank you.
Thank you for the presentation. So let's start the Q&A session about 4 minutes. Please send the question to the chat box or push the raise hand button for oral question. Any question or comment? If not, I may ask some question.
See some audience raising the hand.
Okay. Professor Yap.
Okay, yes. My question was, I listened to all the things. Were there also findings where I would say so surprising to the Go world that they said we have never seen, no, not this move, but this, I would say, new idea?
No, not in these endgame positions. There's no surprises there. The moves are all super simple.
Yeah, I understand. It is only unexpected moves, but not a new idea in the end game, so to speak.
No, I mean, these are positions where we understand optimal play from the mathematical theory. So any surprises would be the only surprises were the mistakes that it makes.
Yeah. Okay. Yes.
Okay. Any other questions?
Do you expect or do you hope for surprises in the future? Because not everything is clear at the moment in the end games in Go. Yes. So you shift slowly the boundaries a little bit to the more difficult positions. And the question is now, when come there positions which have not been, I would say, analyzed, or have not been seen, or have not been discovered by human beings?
Yes, I certainly can see, well, we can give you some positions where the current programs cannot solve them because the combination of policy and search is not strong enough. And yeah, we hope that these will provide an incentive for people to improve their software even further.
Okay, I wish you much success with finding that solutions and positions.
All right, thank you.
Okay, so another question on the Q&A button. On the meta level or at a higher level of abstraction, can you provide insights or hypotheses? What type of limitations KataGo has? Why does the AlphaZero architecture also with search have these limitations?
Right, so one clear case that we found that surprised us, that it really seems to like capturing stones more than making a simpler move that does not capture stones, even if the simpler move is worth slightly more. So there are some surprisingly simple cases where you can capture a stone, it's worth 2 points, or you can make another move that's worth 2 points plus some epsilon, and the policy always likes capturing stones. So I suspect that's an artifact from what it learned early on in the training, that capturing stones is good. So from what we see, it still has a bias towards capturing stones that is not justified by the true value of the move.
Okay, thank you for the questions and the answers. So the next presentation is solving linear NoGo with combinatorial game theory by Haoyu. Please share the presentation and start.
Hi, can you see my screen and hear me okay?
Yes.
Okay, great. Then I'll begin. Hello, everyone. I will present our work on solving linear NoGo with combinatorial game theory. Let's begin by introducing the game of NoGo. NoGo is a variant of the game of Go. It shares the same concepts of blocks and liberties as in Go. What is different from Go is that in NoGo, all blocks must have at least one liberty. So capturing moves and suicide moves in Go are not allowed in NoGo. The game ends when a player has no move to make, and that player loses the game. And these rules makes NoGo a normal play game, and it is suitable for combinatorial game analysis. Linear NoGo refers to the NoGo game played on 1x(n) board, as shown in the example below. In terms of notation, we use X to represent a black stone, O for a white stone, and a dot for an empty point. So the board can be represented as a string of X, O, and dot. Several works have already explored the idea of combining search algorithms with combinatorial game theory, or CGT, to solve games. For example, here we have solving Go endgames, Amazons, and Clobber. But this approach had not been applied on solving NoGo. And that's what we're gonna do. The first two works listed on this page are on solving NoGo from Shih and Kasnav. They both solved up to 5x5 NoGo, but no CGT was involved. The third work is from Shen, his PhD thesis. In that work, he did use CGT to analyze NoGo positions. For example, he had calculated the mean and temperature of many positions. He also proved several theorems on board partitioning into independent subgames for 2D NoGo. But no solving was involved in his work. Here's another one from us. In this work, we solved all NoGo positions with up to 27 points. And to achieve that, we designed a new solver called the SPH solver. It is a traditional Boolean Nagamax solver with two heuristics and an SPH transposition table. It does not have any CGT enhancements. And that's all for previous work. What's new in our current work? And in this work, we developed a new solver for linear NoGo. It is called the CGT solver. It combines Boolean EGMX with several CGT-inspired enhancements. I will first introduce two important properties of linear NoGo. There are block simplification and exosplit. I will prove these properties or theorems with combinatorial game theory. These two properties form the basis of our CGT enhancements. After that, I will describe some additional components that further improve the performance of the solver. Okay, let's begin with block simplification. The theorem states that a block of stones of the same color can be replaced by a single stone of that color. As you can see in the example, on the left is the original board. It has two blocks of black stones. Both of them are replaced by a single black stone on the right. The proof is straightforward. So simplification does not change liberties. So the set of legal moves does not change before and after the simplification. And it also means that if you draw the game tree, the new game tree is actually isomorphic to the original one. And by isomorphism, CGT tells us that the two games are equal. Next is exosplit. The theorem states that a linear NoGo game can be split into two independent subgames at the boundary between two blocks of opposite colors. In the example below, on the left is the original board, and you can see there's an XO pattern in it. We can split the game at that boundary into two subgames on the right. And the intuition behind the proof is that a move played on the left does not change the liberty and therefore the set of legal moves on the right, and vice versa. Again, if you consider all possible continuation of the two games, they're the same. So the two games are equal. Here I want to show an example of block simplification and XO split working together. It also introduces another CGT-inspired trick, which is the cancellation of subgames. From the first line to the second line, we do block simplifications. And from the second line to the third line, we do XO splits. Here I want to point it out that in the third line, we have two subgames. One is x dot dot x, and the other is o dot dot o. And you can see they're inverse of each other. So actually they get canceled. They both go away. And the final result in the fourth line, you can see is much simpler and much shorter than the original game in the first line. So using block simplification and XO split, we can reduce both the breadth and the depth of the search tree. Here's a definition of reduced position. We call a linear NoGo position a reduced position if neither block simplification nor XO split can be applied. On this slide, I want to show the comparison of search trees. On the left is a classical search tree, and on the right is a search tree generated by our CGT solver on the same position, same game. I want to emphasize that a node in our CGT solver's tree consists of multiple subgames, and those subgames can also have variable lengths. This is in contrast with the classical search tree in which a node has a single board of a fixed size. Now let's talk about the additional components of the CGT solver. The first one is static evaluation. Static evaluation tries to catch early results by CGT analysis when it is possible. Let's look at the example here. The original game G is equal to H1 plus H2 plus H3. Suppose we know the outcome class of H1 is N, so H1 is an N position, and H2 is a P position, R position, and H3 is a P position. By CGT, we know that N plus R plus P equals to N plus R. P position goes away. And also by CGT, if we look at this new position, N plus R, if white goes next, we can immediately know without search that white can win. So static evaluation can save search effort. Of course, this raises the question of how can we know the outcome class of those simple games beforehand? And the answer is we build a database. I'll talk about how to build a pre-computed database and what the database contains. But before that, let me introduce another theorem. This theorem states that for n greater than 0, there are 3 to the power of n plus 1 distinct reduced positions with exactly n empty points. Instead of going through the proof, I'll give an example here. Let's try to enumerate all reduced positions with exactly 3 empty points. A reduced position means that a stone must be surrounded by empty points, because otherwise we can do block simplification or axial split. So we can enumerate positions by inserting stones between empty points. Let's look at this template here. An underscore means you can insert a black stone or a white stone there. Of course, you can also choose to insert nothing. So there are 4 insertion points. And each insertion point has 3 options, a black stone or white stone or nothing. So in total, we have 3 to the power of 4 reduced positions with exactly 3 empty points. And from the previous theorem, we know how to enumerate reduced positions. Then to build the database, we simply organize it by layers. Each layer contains all reduced positions with a particular number of empty points. And we use the previous theorem to find all those positions at a given layer. In the end, our database contains all reduced positions with up to 15 empty points. For each entry in the database, it contains 3 elements, the corresponding board, the outcome class, and a pointer to the simplest equal game. The simplest equal game of a position G is defined to be the game that is equal to G and also appears earliest in the database. In the example below, here's the original game G and its simplest equal game S of G. And you can see S of G is much simpler than the original game. During search, we will replace each subgame in the node by its simplest equal game, if it exists in the database. So this is another trick, this simplest equal game replacing trick. It can reduce both the depth and the breadth of the search tree. So how do we find simplest equal games when building the database? For position G, we sequentially test for all games H before it in the database. If G minus H equals 0. If it does, then we know H is the simplest equal game for G. Lastly, I'll describe the transportation table used in our solver. Recall that a node in our CGT solver's tree is a sum of multiple subgames, and each subgame has a variable length. But popular hashing method like Zorbest hashing assumes a single board as input. So in order to hash a node of some games, we need to convert it into a normal form. And we do that by encoding the board of each subgames as a string. We then sort those strings into some deterministic ordering. Finally, we concatenate the sorted strings with separator symbols in between. And this gives us the normal form of the node. We can then apply Zorbest hashing on this normal form. Yeah, and that's about our new solver. From now on, I want to talk about our experiment results. In our previous work, we solved linear NoGo up to 1/27. And this time with the CGT solver, we were able to get 12 new results from 28 to 39. And we proved that they're all actually winning positions for black. Black can win by playing B1 as its opening move. These new findings extend our conjecture in the previous work that black players can maybe always win large linear NoGo positions with B1 opening. In the figure below, I present their results on opening moves. That is, if black plays here, can black win? A black stone indicates a winning opening move, and a white stone indicates a losing opening move. And you can see the pattern on large linear NoGo game is quite consistent. We also compare the new CGT solver with our old SPH solver. Figure on the left shows the comparison in terms of node counts, and figures on the right shows the solving time in seconds. Y-axis in both figures are log10 scaled. As you can see, the CGT solver needs 2 orders of magnitude fewer nodes than the SPH solver. And so the CGT solver is much more efficient. Also note that its runtime is faster than by a similar ratio. So it means that the CGT-based enhancements actually do not add much overhead to the main search algorithm. And please also note that in this figure on the right, the gap between the SPH solver and the CGT solver, the 2 curves, actually getting wider as the board size increases. So the CGT solver actually really shows its potential on large linear no-go game. We also did an ablation study. Each subplot here shows the performance of the CGT solver after we remove one of its components. The evaluation metric is in node counts. The transposition table, seen here, gives the largest improvements as expected. The simplest equal game replacing scheme also improves the performance by a constant factor. And surprisingly, the effect of static evaluation diminishes quickly when the board size increases. On this slide, I want to show some statistics on the search tree generated by the CGT solver when solving 1/30 no-go. Figure on the left shows the distribution of nodes and leaf nodes across steps. I want to point out that the earliest leaf node appears at the depth of 4. And if you consider a traditional search tree, you have to play to the very end of the game to encounter a leaf node. But in our CGT search tree, the leaf node appears much, much earlier. So this confirms that the CGT enhancements we have can reduce the depth of the search tree. And this phenomenon partially explains why our new solver is much more efficient than the old one. And finally, conclusions. So we get 12 new results on solving linear no-go, namely from a board size of 28 to 39. And we build a new solver, a CGT enhanced solver. And there are more statistics and implementation details in the paper. For example, we have a heuristic called play in the middle, but I didn't talk about it. As for future work, I think it would be interesting to extend this work into solving 2D no-go. For example, block simplification works for 2D no-go if you consider the board as an abstract graph. As for exosplit, similar decomposition rules for 2D no-go has been proposed in Shan's PhD thesis. So solving 2D no-go could be a next step. And that's the end of my talk. Thank you.
Thank you for the presentation and keeping the time. So let's start the Q&A session. Please send the question to the chat box on the Q&A or please raise your hand. So the simple question, you solved to 39 lengths, but you showed only the opening moves under 34. Please show the opening move from 34 to 39 if possible.
So actually, due to computation constraints, we didn't get all those results before the deadline. But we believe that, so this pattern is very consistent. So we believe the results will be similar. So on even boards shown here, it's always the case that the two endpoints are losing move. And for uneven boards, the two middle points are losing move. We have proved the two middle points are losing move in our previous work. And for odd boards, I think other than the two ends, every move is a winning opening move. Yeah, but we haven't proved it yet.
Okay, thank you. So the question in the chat box, why static evaluation did not help to reduce nodes for bigger boards? You said surprisingly, but we don't know the reasons.
Yeah, so actually, I haven't get down to the bottom of this issue as well. But my conjecture is that so we do scale up the board size, but we didn't scale up our database. The database is a fixed size, a pre-computed. So I guess that's why the kind of how useful this static evaluation is, because it depends on the database and what the game's in the database. Since we didn't scale up the database, then its effect will diminishes. But that's just my guess. Yeah.
Okay, thank you. Any other question? I think this target 1 by n NoGo is very, how to say, eccentric game, special game. So what is special to this game? The CGT solver is something is special to this game and something is general. How to apply your ideas to other games?
Okay. So I guess the true power behind combinatorial game analysis, the CGT part, is we really want to split the game into multiple independent subgames. And for some other games, I think we can do the similar trick. For NoGo, since this one is only about linear NoGo, and it's quite simple to see, but for 2D NoGo, actually in Shen's PhD thesis, he actually proposed many decomposition rules about it, how to split 2D NoGo into independent subgames. And so here we have some previous work using the same technique. For example, in clobber, when you clobber a stone, and that point becomes the original point becomes an empty point, and then you can split the clobber, the very long clobber string, into multiple independent parts, and that also gives huge performance improvement. So what's general for the games, I guess, is really this idea, like use CGT to decompose positions and to solve from there. Yes, I guess that's the core message we want to convey.
Yeah. For example, to which games?
Sorry?
For example, which games are good target for your next target? Using CGT solver's IDs.
I guess for my next step, I will think about how to solve 2D NoGo.
2D NoGo.
But for other games, sorry, I don't have anything in mind right now.
Okay, thank you. So, no more question or comment? Okay, so let's go to the next presentation. Thank you for your presentation. Okay, the last one is solving 7x7 Killall-Go with the Seki database presented by Yun-Jui Tsai. Okay, if you are ready, please start.
Yeah, I'm ready. So, hello everyone, I'm here to report this paper, solving 7x7 Killall-Go with Seki database. And my name is Yun-Jui Tsai, and the author of this paper. And I'm from National Yangming Jiaotong University in Taiwan. And this is the outline of the presentation today. 7x7 Killall-Go is a variant of Go. The basic rule is the same as Go, but in 7x7 Killall-Go, black plays 2 stones first, so black is given a large advantage. Accordingly, black need to kill all the other white stones to win, and white only need to secure a single safe area to win. To detect whether an area is safe by program, we could use Benson algorithm. For a Benson area, the block is guaranteed to be safe from capture, and even if the opponent is allowed an unlimited number of consecutive turns. And this is an example of Benson area. Another winning condition of white is to secure a Seki area. Seki is a situation of coexistence. In the Seki area, whichever players plays inside the region, the green region, renders their stone vulnerable for capture. So let's look at this Seki position. We can see that in this region, if white plays first, black can capture all the white stones. In another way, if black plays first in this region, white can form Benson and win. So this is an example of Seki. And in this slide, we are going to introduce some example of Seki in standard Go. For case A, B, and C are local Sekis. The Seki area only covers a single block on the board. And case D is an example of global Seki. The result might be effective when its surrounding condition changes. So the region may even be the whole board. But in 7x7 Killall-Go, because black plays 2 stones first, so the Seki shape opens like the white securing an area and black occupying the boundary of the white area, while also attempting to capture the white stone inside the region. So that's the case A. And for case B and C, because in Killall-Go, I only require to secure one Benson area. So for case B and C, there contains a Benson area outside the Seki region. So this kind of Seki would not appear in 7x7 Killall-Go. And in this paper, we only consider type A and skip the case of global Seki. So let us move on to the solving process of 7x7 Killall-Go. We could find that if we could not recognize Seki and only use Benson as terminal condition, once we encounter a Seki position, the game would not terminate immediately, and black would move outside the region to postpone white's victory. And even in this situation, the game is still not terminated, and until white suicide in this region, and white secure Benson area, finally again terminate. So without Seki, the depth of the search tree will be too deep to be finished, and even a simple Seki position could not be solved within a day. So to get rid of the unnecessary search, we should recognize Seki position earlier by program. In the previous work, recognizing Seki in Comparative, they propose algorithms for recognize global and local Seki. And for local Seki, they use the DFPN twice to prove that whichever players play inside the Seki region first will make their stones be captured. So after knowing how to recognizing Seki, we can start to building the Seki solver. To build a Seki solver that can terminate at Seki position, a kind of solution is to search Seki situation during solving after each move. However, the algorithm of recognizing Seki takes time during solving and will make the solving process slower. So to deal with this issue, we could ask that, could we save the search time in solving? So to save the Seki search time in solving, in this paper, we aim to build a Seki database. So we generate an amount of Seki patterns before starting solving, and then store the Seki pattern into a Seki database. By doing so, during solving, we can query the database after each move and return a Seki position immediately. It do not need a large time to search Seki. Next, in Master, we are going to introduce how we build a Seki database. The first step to build a Seki database is to generate all the permutation of patterns from area size 5 to 8, and that is the pink shadow area. After the area is determined, we surround the area with white stone and then black stone. And then finally, we fill the area with black stones until only 2 or 3 liberties remain. And these are possible Seki patterns. Next step, for a possible Seki pattern, we need to verify whether it is a real Seki pattern. The goal is to prove that whichever players play inside the Seki area will make their stone be captured. So we first prove that white will lose if white plays first, and black will lose if black goes first. So after that, we can confirm that this pattern is a Seki pattern. Once the pattern is confirmed as a Seki, we then save it into our Seki database. And here we only save the back stone positions and empty stone positions inside the area. Okay, now for another instance, if the pattern is not a Seki pattern, here we found that back will win if back goes first. So this pattern is not a Seki pattern. So we discard it and do not store it into our database. Okay, so when solving, we can query the database after each move. And we can check that the region of the next action and search whether this area is a Seki position by match the patterns inside the Seki database. So for instance, if we find an area that perfectly matches the patterns in a database, we can return the Seki position immediately. And if the patterns do not match, the position is not a Seki position. Let's move on to the experiment part. In the experiment, we first did the information of Seki database generation. And in the following experiment, we use the database of area size from 5 to 8, and which nearly has 250,000 patterns. And in the next experiment, we try to solve the Killall-Go openings using an online fine-tuning solver. The online fine-tuning solver is a manager worker system that uses totally 9 1080s, and each solver is a MTS solver that uses PCN to provide search heuristics. And in the previous work, they only use Benson as the terminal condition for solver. So in the following experiment, we apply Seki database into the solver, and therefore Seki will be another terminal condition for this solver. To show the enhancement given by Seki database, we pick 10 benchmark problems for solving. The benchmark problems can be separated into 3 parts. For problems A and B, there are problems suggested by Go experts. So with a high probability of Seki occurring. And for problems C to H are problems that are collected during self-play, which can be solved without Seki database. And finally, opening 1 and 2 are frequently used openings in 7x7 Killall-Go. Okay, so for case A and B, Seki is inevitable. When not using Seki database, case A and B cannot be solved within a day. However, after using the Seki database, they can be solved in nearly 500 and 6,000 seconds respectively. And the Seki database is very useful in this kind of openings. Next, for problem C to E, there are openings that can be solved even without the Seki database. However, using the database gives a 20% to 50% discount on solving time. And for problem F to H, Seki database gives at least 20% discount. And finally, for openings 1 and 2, these are frequently used openings in 7x7 Killall-Go. And we can find that utilizing Seki database also gives a discount for nearly 10% and 20% discount for time. And this shows that the database can still be useful when solving some typical openings. Even Seki may not be the part of the solution. So overall, the database still provides benefits. For conclusion, in this paper, we built a Seki database that significantly solving time. And even for common Seki openings in 7x7 Killall-Go, the Seki database also give a 10% to 20% discount on solving time and nodes. And for openings that Seki is inevitable, previously unsolved Seki position, that is the case A in our benchmarks, that can now be solved in just 482 seconds. So that is a huge improvement. So in the future, the database could be extended to cover global Seki and even be applied to other Engen database and other related fields. So that's my presentation today. Thank you.
Thank you for the presentation. We have much time for discussion about 6 or 7 minutes. So any questions and comments? First, I want to confirm the definition of solving rate in the paper. I don't understand where the solving rate in table 3 in the paper.
Table 3.
Not in this today's presentation, but you compute the solving rate of opening.
In which page?
In page 9.
Oh.
Not today's presentation, but the conference paper.
Oh,
table 3.
Okay, so for solving rate, and in that experiment, we think to the job that sent to the worker solver, and we find that we calculate the solving rate of the worker, and the worker is a MTH solver that limit the node. So if the node limitation is reached and the problem still be unsolved.
Okay, thank you.
We can calculate the solving rate. Yeah.
Okay. The question from audience. It seems difficult to extend the database to global Seki. How would you approach this?
Okay, so in our Seki database, the patterns in our database is limited to how we generate a pattern. So to extend to global Seki, we need to first find a new method to generate possible Seki patterns of global Seki. And after we can generate some possible Seki patterns for global Seki, I think we can finally generate a database with global Seki.
By the way, in this game, is it frequent to happen the global Seki?
In this experiment, the global Seki is ignored, and in 7x7 Killall-Go, global Seki will not occur frequently, so it will not influence our efficiency.
Okay, thank you.
Thank you.
Another question. You said the non-Seki positions are discarded, but would storing non-Seki positions to another database further help speed up?
If a pattern that is not a Seki we will not store it into our database.
Yeah, but for example, this shape is very famous and frequent dead pattern. A dead
Yes.
pattern or alive pattern can be used for speeding up the search, I guess.
Yes. So here we only store the area inside the Seki region. So this pattern, if we use this pattern in our database, if the pattern is matched, we could find that the region is at least Seki. And even if this pattern is not accurate Seki, and why still can win this game? So I think the step out may occur even the Seki is not only solution.
Yeah, it's not so easy to terminate the search if a dead pattern is found because the surrounding black stones are maybe weak. But if a live pattern is found, I think the search can be stopped.
Yes. I think some alive pattern can be solved in database. But in that situation, I think the boundary or the surrounding condition may also need to be solved. It may also need to be stored into the database.
Okay, thank you.
If some alive pattern. Yeah.
Another question, sorry, I missed. Can you elaborate on the implementation of the Seki database? Has a hash key does not need to use all features, but only the most important ones for encoding. Can you go into further details? Implementation of Seki database. Only simple matching or any hash or something?
Any hash. And so in this work, we only store back position and empty solution. So I think it's only the only one circumstance of the pattern. So I think the hash key is not required.
It's not required. Okay, so it's time to close this session. Thank you for all participants, especially to ask questions and present excellent results. Thank you. So let's close the session. See you tomorrow.
Yes, thank you for all presenters in session 2, and also thank Professor Ikeda for hosting the session. And day 2 will start roughly 27 hours later, so see you tomorrow.
Thank you, everyone.